So far, we've considered how insufficiently rapid mass transport in reacting systems can impact measured rates. Since reactions can liberate or consume significant amounts of energy, heat transfer in these systems must also be considered. Luckily, there's close analogy between heat and mass transport processes, so we can use a similar approach as we have been using to consider heat transfer. So let's look at a flat plate catalyst pellet with a first order reaction A goes to B occurring and try to find the effectiveness factor for a non-isothermal situation. So this will involve writing material and energy balances and solving them simultaneously. We can write a steady state mole balance on a differential slice through our slab, and this will describe the flux into this volume element by diffusion minus the flux out plus the rate of generation of A within that control volume. And the sum of these terms will be equal to 0 if we're operating at steady state. So our mole balance will look like this, where our flux terms are multiplied by cross-sectional area, since they have units of moles per second per unit area, and our reaction term is multiplied by the cross-sectional area times the thickness of that differential element, since the rate depends on the volume available for reaction. So if we divide through by the cross-sectional area times delta x, and then take the limit as delta x goes to 0, so the slice becomes infinitesimally thin, our mole balance becomes this differential equation. We can write the flux of A, Na, using Fick's first law. Here the effective diffusivity of A is used, since the entire cross-sectional area of the slab is not available for diffusion, and the pores through this material are not straight. Substituting this equation for our flux into the mole balance gives us this second order differential equation. So here our reaction rate constant K, and to a lesser extent the concentration and diffusivity, are functions of temperatures that will couple this expression to our energy balance. So we can similarly write an energy balance on this differential slice, and once we divide by the cross-sectional area and take the limit as the slice becomes infinitesimally thin, we can arrive at the following differential equation. Here Q is our heat flux, and delta H of reaction is greater than 0 if we have an endothermic reaction and less than 0 for an exothermic reaction. The heat flux can be related to the temperature gradient using Fourier's law. And here lambda is the effective thermal conductivity. Plugging in this expression for our heat flux into our energy balance, we can come up with this second order differential equation to describe changes in temperature. So this energy balance can be coupled to our material balance. We can write our rate constant in some Arrhenius type relationship as a function of temperature, and then these two balances can be solved simultaneously. The differential equations will be subject to the following boundary conditions, so we can write that the temperature is going to be equal to the surface temperature at x equals xp, so this is at the edge of our slab, and at that position our concentration is going to be equal to the surface concentration. The second set of boundary conditions are symmetry boundary conditions. So for this geometry, the temperature and concentration gradients must fall to 0 at the center of our slab. So the effectiveness factor, which again is going to be equal to the rate observed or evaluated under the real conditions at the reaction medium, divided by the rate we would observe in the absence of concentration or temperature gradients if the entire slab here saw the surface temperature and concentration of A. And so this effectiveness factor is typically calculated for different values of certain dimensionless parameters. So the first of these is the Arrhenius number, gamma. This quantifies the reaction's sensitivity to temperature. The Thiele modulus, which for this geometry is the half thickness of the slab squared, times the reaction rate constant evaluated at the surface temperature divided by the effective diffusivity of A, all to the 1/2. And this quantifies the relative rates of reaction compared to diffusion. And our last dimensionless number is the Prater number, which quantifies the dimensionless maximum temperature rise in the pellet. So here let's look at a plot of our effectiveness factor versus different dimensionless parameters. Let's first consider the case of a Prater number equal to 0. So this is the isothermal case that we've considered previously. So the effectiveness factor will look something like this, where at very low Thiele modulus, we have an effectiveness factor equal to 1, and the effectiveness factor drops as the Thiele modulus becomes larger. Similarly, if we have a beta value less than 0, if we have an endothermic reaction, we'll never have an effectiveness factor greater than 1. So the observed reaction rate will always be equal to or lower than that we would observe without any gradients, because the temperature is going to be lower than that in the bulk. If we now look at Prater numbers greater than 0, if we have an exothermic reaction, we now get effectiveness factors that can be significantly larger than 1. And as the beta value increases, so the reaction becomes more exothermic, we can get even higher values. So if we remind ourselves of the definition of the effectiveness factor, it's the rate at the actual concentration and temperature inside the catalyst particle divided by the rate we would observe if the entirety of the particle was at the same concentration and temperature as the surface. So here, if we have a strongly exothermic reaction, the temperature and consequently the rate can be much higher within the catalyst pellet than what we would expect based on the surface or bulk fluid conditions. So here we've briefly seen that it's important to consider heat transfer in systems involving coupled reaction and transport. This is done by solving coupled material and energy balances. So since rate constants depend strongly on temperatures and reactions often generate or sink large amounts of heat, temperature gradients in porous catalyst particles can be significant and have an important influence on measured rates.